Now, for those of you who would like more information, you might want to go down to your local bookstore or wherever you can purchase magazines. And this particular subject or topic is a feature article in the May edition of Sky and Telescope magazine. And maybe some of you even subscribe to Sky and Telescope. It's one of the best popular glossies on the subject of astronomy, and read by tens of thousands of both amateur hobbyists and also professional astronomers around the world. So, this story, this rather compelling story, began 92 years ago this month and involves these two gentlemen. The person you see on the left is Arnold Schwassmann, and the person on the right is Arno. I don't know if I've ever met anybody named Arno, but this is, after all, about two German people, German astronomers, Arno Wachmann. So we have Schwassmann on the left, Wachmann on the right, and in May of 1930, they discovered a comet. Now, these two guys were the dynamic duo of the observatory in Hamburg. They discovered not just comets, they also discovered other things, asteroids, a new star. This particular comet that they discovered was the third that bears their name. They discovered four comets. The fourth one they shared with another gentleman, an American by the name of Leslie Peltier. But the first three comets that they discovered were known simply as Schwassmann Wachmann. Schwassmann Wachmann 1, Schwassmann Wachmann 2, and this was Schwassmann Wachmann 3. By the way, every so often, you're going to hear me pause for a few seconds. It's just so that I can get a swig of Poland spring water to help lubricate my vocal cords here. Anyway, this comet number 3, discovered by these two gentlemen, Schwassmann and Wachmann, and from here on, I'm not going to refer to it as Schwassmann-Wachmann 3. I'm going to simply say SW3. So SW3 is discovered, and after a few weeks, they discover that after doing an orbital computation, that this comet is going to pass relatively close to the Earth. In fact, the distance on May 31st of 1930 was 5,735,400 miles away. Again, let me stress, comets that come that close to the Earth are few and far between, and when they do come that close to the Earth, usually they're either quite bright and spectacular or at the very least quite interesting. We did, in the last 40 years, have a couple of comets that did come rather close to the Earth. This one, maybe some of you might remember if you've been in the hobby for a long time, in May of 1983, this was Comet Iris-Araki-Alcock. And this comet came within 2.9 million miles of the Earth, second closest approach in modern history of a comet to the Earth. Now, this was one of those cases where it was not a spectacular comet, but it was an interesting comet. It moved across the sky very, very rapidly. I remember, in fact, being at the Custer Institute. Maybe some of you know what that is. It's out in eastern Long Island in Southold. And and they have an observatory out there. And I was at the Custer Institute on the night when this comet was passing closest to the Earth. You could look through a telescope, and the comet actually seemed to move relative to the background stars. That doesn't usually happen. But the comet was so very close, it looked almost like you were watching the minute hand of a clock, moving very slowly against the background stars. It became as bright as the North Star, second magnitude, and looked like a fuzzy ball. Again, over a course of a few nights, it moved from one end of the sky to the other. That was Iris-Araki-Alcock. Then 13 years later, we had another comet that came rather close to the Earth. Not as close as Iris-Araki-Alcock. This comet in March of 1996 was known as Comet Hyakutake. Hyakutake, discovered by a Japanese observer, came within 9 million miles of the Earth. And it was so close and also was a bit larger and a bit brighter than Iris-Araki-Alcock. So this comet was quite bright, as bright as the brightest stars in the sky. And if you were far away from the lights of a big city, I mean, where the skies are really dark and where you could see a lot of stars, The tail of the comet stretched well, way across the sky. A friend of mine and I was living at the time in Levittown. He was living in North Merrick. Together, we made a plan that on the night that this comet came closest to the Earth, I would pick my friend up in my minivan, and we drove to the north up to a little community in Dutchess County, New York, called Hopewell Junction, where the skies were quite dark. We took about an hour and a half to get up there, and when we did get up there, and I stepped out of the van along with my friend, we looked up and we saw this comet with the head or coma of the comet shining brightly near the North Star and a long trail of gas which stretched across, well, almost halfway across the sky. It was an amazing sight. And I turned to my friend and I said, well, you don't see this very often, or you don't see this every day or night of the week. That was Comet Hyakutake. It was indeed a big, big hit for those who looked for it. It was a spectacular comet in the spring of 1996. Here is a picture which should be familiar at first glance. That is the top or the upper floor of the or the upper spiral of the Empire State Building. Up here, I guess, is where the 86th floor observation deck is. But I want you to take a look at this. See that little fuzzy blob right next to the Empire State Building? This picture was taken from 29th Street and Avenue of the Americas in the middle of Midtown Manhattan, in the middle of probably one of the most light polluted areas of the world. And yet, this picture shows clearly that the comet was able to cut through the light pollution. Maybe not the tail, but certainly the head was evident right next to the Empire State Building. So you see, comets that come very close to the Earth, again, could be quite spectacular, like Hyakutake, or at least quite interesting, like Comet Iris-Arakiokac flying quickly across the sky. Everybody was hoping back in 1930 that that would be the same for Comet SW3, Schwassmann Wachmann 3. But alas, this comet, unlike the others, was very, very small. A piece of stone with some volatile material associated with it, no more than maybe a mile, mile and a half in diameter, very small, even as comets go. And when the comet came closest to the Earth on the night of May 31st of 1930, it still was not visible to the unaided eye. You needed good binoculars or a small telescope to see it. So it really was not very spectacular. But a comet is a comet. This one was coming close to the Earth. And observatories around the world made plans to observe it with their various instruments. What you're seeing on the screen now is the Yerkes Observatory Telescope out in Wisconsin. This is the biggest, still the biggest, refracting telescope in the world. And this particular telescope, back in 1930, the observatory had a number of people on staff. One of them was an immigrant from Belgium who came to the United States, came to the Americas. His name was George Van Beesbroek. His good friends simply referred to him as Van B. Well, Van B, on the staff of the Yerkes Observatory, this was his specialty. This was right in his wheelhouse, so to speak. He loved observing comets and other small bodies of the solar system like asteroids. So this comet coming very close to the Earth, Van B was at the observatory observing it and photographing it every single night that it was visible. This is an amazing picture to me. I mean, some of us in the hobby, some of us in astronomy have reasonably large telescopes. I myself have a 10-inch reflecting telescope, a Dobsonian reflector. But can you imagine having free and ready access to the biggest refracting telescope in the world? Van B did, and he did observe Comet SW3. He took pictures of it. This, what you see here, doesn't mean 10 feet. This is 10 minutes of arc. This was a couple of weeks before the comet came closest to the Earth. And this comet subtended in the sky at this particular point in its apparition about 2/3 of the apparent size of the full moon. And when it was closest, Van B took a good hard look at the center of the comet, and he saw the nucleus. that teeny tiny mile and a half piece of rock, it appeared to him as if it were like an edge-on spiral galaxy, and it looked to him like a spindle-shaped object. Amazing, absolutely amazing. So, yes, the comet was not spectacular. Yes, it wasn't visible to the eye and only visible to those who knew where to look with telescopes and binoculars, but still an interesting object. And after May 31st, after it made its closest approach to the Earth, the comet went back out into space. It goes around the sun every 5.5 years. And yet, with that small orbit, the comet, after 1930, was missing in action. These are the presumed dates of when the comet made its closest approach to the sun: 1935, 1941, 46, all of these dates, and yet all of these times, the comet was never visible. The comet was never seen. They looked for it, couldn't find it, and the comet again was missing for a good half century or so. 1979, we finally saw it. Hip, hip, hooray! But then in 1985, the comet passed too near the sun and wasn't really readily accessible. So all of these years of the time when the comet was closest to the sun and also passing by the Earth, we missed out. Why? Why? Well, as I just told you, this comet is a piddling little thing. It's a very dim comet, a very faint comet. But here's another reason why. It was because of this big guy. This is Jupiter, the biggest planet in the solar system, 11 times the size of the Earth, 1,300 times more massive than our Earth, and with a large gravitational field. So little comets like SW3, when it passes near to Jupiter, what happens is that Jupiter uses its great gravitational force, grabs onto the comet, and kind of pulls it or tugs at it and places it in a new orbit. Now, if you're working with an old orbit or the latest possible calculated orbit for a comet like SW3, Jupiter comes along and changes the orbit slightly, you're looking in the wrong direction for this comet. And again, you're handicapped by the fact that it was a small object to begin with. Jupiter has not just done this to SW3. We estimate or guesstimate that there must be as many as 400 small comets, tiny comets like SW3, that are in the general area between Mars and Jupiter. This is the orbit of Mars right here, and this is the orbit of Jupiter. And thanks to Jupiter's gravitational force, it has captured these tiny comets and placed them in orbits in a, generally speaking, 6 to 12 year interval or 6 to 12 year periods around the sun. We think that there may be as many as 400 of these kind of comets, and so we call comets that are locked in these orbits a member of Jupiter's family of comets, because again, Jupiter was the main reason why the comets are in this particular place in the solar system. And SW3, Schwassmann Wachmann 3, is a card-carrying member of Jupiter's comet family. Well, anyway, in 1990, the comet came back. In fact, it came within about 30 million miles of the Earth, and it was the most favorable apparition, the most favorable view that we have had of this comet, going all the way back to 1930. So there you see it there. Then the comet was expected to come back in the fall of 1995, but now the story takes a different turn. And it takes a turn starting with this. This is one of the great radio telescopes of the world. This is the Nan-K radio telescope right outside of the observatory in Paris, France. This radio telescope got hold of Comet SW3. They began to investigate it with the radio telescope, and investigating the emissions that the comet gave off. And the chemical or gaseous emissions given off by this comet in 1995, it was in September, began to increase rather rapidly. In fact, so much so that one of the chemicals, the hydroxyl radical, I'm now talking in, for those of you who remember your high school chemistry, the hydroxyl radical was spiking. And this was very unusual. I mean, the gases that were being emitted by this comet were suddenly going off the chart, so to speak. what was happening. And now, in addition to the gases increasing, the comet itself started to increase in brightness. It began to get rather bright, much brighter than it had been expected. Over in Massachusetts at the Smithsonian Observatory, which is where the Central Bureau of Astronomical Telegrams is located, they had to put out what is called an ephemeris. This is a finding ephemeris to help amateur and professional astronomers locate celestial objects like asteroids and new stars that might flare into view like nova and comets. And in this particular case, for this ephemeris, the Smithsonian Observatory noted that the Bureau has received numerous reports from observers worldwide of independent discoveries of this comet, which has continued its remarkable outburst in brightness. In other words, there were people who were emailing, calling, or, Lord, back then still people were doing this, sending telegrams to the observatory saying that, hey, we think we discovered a comet. Now imagine, if you will, the following. You're outside with your telescope. This is now October of 1995. And you're getting ready for a night of observing. You're getting ready to spend a night under the stars and look at a number of different celestial objects. The sky gets dark, and as you look toward the western part of the sky, you do a double take. You say, oh, what is that? My goodness, what is that? And you train a pair of binoculars on it, and then you look at it with a telescope, and you say, oh my goodness, that's a comet. It's a comet that's visible even with my bare eyes. I don't even need a telescope or binoculars to see it. What? And then you quickly thumb through your latest edition of Sky and Telescope magazine. Well, then you take your laptop and start checking the internet. Was there supposed to be a comet in the sky tonight that I didn't know of? And apparently there wasn't. And then you suddenly say to yourself, oh my goodness, I have to tell the Central Bureau for Astronomical Telegrams in Massachusetts that I discovered a comet, a new comet. But no, this isn't a new comet. This is SW3. And that's incredible. That's amazing. And I'll tell you why it was amazing. In 65 years earlier, when it was discovered in 1930, the comet was literally right up next to the Earth, less than 6 million miles away, but you couldn't see it because it was so small and dim. You needed binoculars or telescope to see it. Now, on this night in October of 1995, the comet is 122 million miles away, 25 times farther out in space and away from the Earth than it was when it was discovered in 1930. And there it is. There it is for all to see. Binoculars, telescopes, even the unaided eye. My goodness. And people, not just amateurs, but famous professional astronomers like Terry Lovejoy in Australia. He has discovered a few comets of his own. And he made a comment in his logbook that it looked like a mini Halley, a miniature Halley's comet. Its coma displayed a striking parabolic outline. In other words, the head of the comet had an outline that resembled a parabola, and its tail was so intense in its first half degree that the ghostly glow was evident even through horizon haze. So even when the comet was low to the horizon, where it is always a bit hazy, you still were able to see the comet quite well. What was going on? The comet was over 400 times brighter. Why was it bright? Why was it so conspicuous? And in the days and weeks to come, we found out. People looking at it with telescopes noticed that the head of the comet looked rather bloated for whatever reason. And then in December, boom! The comet, what was at once one nuclei, now we suddenly saw 4. The comet had broken apart into 4 separate pieces. That is why the comet looks so bright, because in the process of breaking up, a tremendous amount of dust was sent out into space. A tremendous expulsion of dusty material, and dust is what makes comets bright. Comets are composed of gas and dust. The gas kind of glows faintly, ultraviolet light effects on phosphorescent paint. It glows this bluish color. But dust is a very effective reflector. If a comet is dusty, it's going to reflect sunlight and get very bright. This comet had all of this dust inside. It was kind of like we cracked it open, so to speak. And why did it do this? Why did it break up like this? One theory is that, as I mentioned before, this comet on innumerable occasions passed by Jupiter, and Jupiter would pull on it and tug at it and put it into a new or different type of orbit. And every time it kind of pulled on it and tugged on it and pushed on it, that's stressful. That's especially for a little comet like SW3. And now, when the comet was working its way toward its closest approach to the sun, all of that stress on it, probably the comet just said, "I can't take it anymore," and just broke into those 4 parts, expelling all of that dust and material out into space. Here was the comet in 2001. We still were able to see, using special filtration devices, at least 3 large pieces, but especially in 2006, that was excitement. By 2006, it was no longer 4. There were many, many pieces of many different sizes. Now there were so many, in fact, that they were giving letters of the alphabet to them. This might be A and B and C. Here's D and F and G, J, K, M, O, P. There were numerous pieces. And these pieces, this whole mass of material, was going to pass within 7.5 million miles of the Earth. And now, no longer do we have just observatories here on the ground. We had 2 major telescopes up in space. For example, we have the Hubble Space Telescope in space, and we trained it on these pieces as they passed by the Earth. Here you see fragment B, G, R. But now let's close in on one of those fragments. Let's look at a close-up of fragment B, even closer with the Hubble Space Telescope, and look at what we see here. One singular fragment, when we really close in on it, is breaking up all on its own. Smaller pieces coming off of a large fragment. The comet literally was disintegrating right before our eyes. And then after Hubble was done with it, we used the Spitzer Space Telescope, using its infrared camera, which is why the comet now looks a reddish color. But look, here's one piece, a large piece, and there's another one here, there, and 2 more over here, and a larger piece here, and a larger here, and here. And notice they're all lined up along the orbit of the comet. This comet literally was falling apart. There were over 60, count them, 60 pieces when the comet passed the Earth in 2006, discovered by both the Hubble and by the Spitzer Space Telescope. Now here's the orbit of the comet. The orbit of the comet, as you see as it's moving around the sun, here's where it is out just beyond the orbit of Jupiter. And notice, if you will, that right here, the orbit is such that it's very close to Jupiter. So if Jupiter's in this area right over here, the comet is going to get tugged or pushed or pulled by Jupiter. There's the orbit, and look over here. Now this is real interesting for you and me. Right down here, right there. Here's the orbit of the Earth. This is where we're orbiting the sun, right? But here's the comet orbit right here. And right here at this point, right around the 31st of May in our orbit, the comet's orbit very nearly coincides with the Earth. In other words, Earth and comet, the orbits, are very close together. And that got some astronomers thinking. They said, well, now that this comet is breaking up and disintegrating, now that there are not just one comet, but there's numerous pieces that are traveling along the orbit, is it possible that when we get close to this particular part of our orbit and the comet's orbit, that when we get there, we might intercept or intersect some of that material, which may fall into our atmosphere as shooting stars? Might we see a new meteor shower when we get to this particular orbit, part of our orbit in space? Well, this is not the first time that that concept was brought up. And the other reason why to get excited about this prospect is that this has happened once before. There is a precedent in astronomical history for that. and it involves this comet. This is not SW3, which broke into 4 pieces. This is Comet Biela. And Comet Biela was discovered by a German astronomer, Wilhelm von Biela, back in the 1830s. And in 1842, or 1843, we're not exactly sure of the year, this comet apparently split, fractured, became not, it was no longer one comet, but was now 2 comets traveling side by side out into space. And this is what we saw when we looked toward the comet as it passed on by the Earth and the Sun in 1846. And we saw it like this again in 1852. But then in 1858, when we expected the comet to make a return appearance, or comets to make a return appearance, what happened? No comets. Didn't see it at all. 1865, that was a good year. We felt that that comet would be very favorably placed for observation. We looked again, but no Comet Biela. So what happened? And the general idea was, well, if it split, maybe in the ensuing years, it just completely fell apart. And there's nothing more than just dust, the pulverized remains of the comet, which we will never see again. No, we'll never see the likes of Biela's comet again. Wrong. Because on the night of November 27th, 1872, when the Earth reached that part of its orbit in space where we came by the intersection point, the crossing point of Comet Biela, which we said no longer existed, when we reached that crossing point in 1872 on March 27th, this is what happened. After sunset and the sky darkened, look at that. Look at it. A meteor, not just a meteor shower. This was a full-scale meteor storm. And depending upon who you asked, and depending upon who was counting, people said that meteors fell at the rate of 3,000, 6,000, even maybe as many as 10,000 or more per hour. What a spectacular sight that must have been. So the question is, will we see another meteor display now with SW3, just like what you're seeing here? Well, like I said, with SW3, this isn't the first time anybody considered a meteor shower from it. There was, back in 1930, a Japanese astronomer who did a calculation and said that he thought that the meteors, or proposed meteors from Comet SW3, would intersect the Earth on the night of June 9th in 1930. And sure enough, there was a report that a meteor shower did take place on that night and averaged 60 to 70 shooting stars per hour. But you see, there is a problem accepting this observation. The problem was that, number one, out of all the people, all of the meteor enthusiasts around the world who were looking for meteors that night, there was only one, count them, one single person who claimed to have seen this supposed meteor shower. And he said, well, I have very sensitive eyes. He was able to see meteors so faint, so dim, that most of us, even if we were in a dark sky, probably would not see it. Literally right at the threshold of normal eyesight. But what makes me really suspicious that this guy didn't see it was that he saw it on the night when there was a full moon. And also on the night when we had a big ring or halo around the moon. I'm sure many of you have at one time seen one of these big halos or rings. They usually occur when there's a deck of high, thin ice crystal clouds, cirriform clouds, which produce that ring up in the sky. Now, if you're going to have a full moon and high clouds, you certainly are not going to see many meteors, and especially so if you are claiming that you're seeing meteors on the threshold of normal visibility. So I don't think that this Japanese observer actually did see a meteor shower that night. No, I really, no one else saw it. So a big question mark about that particular astronomical event. Now, all of the ejected particles from a comet, ejected regardless of size and unless perturbed, stay closely confined to the plane of the comet's orbit. In other words, most comets, when they come around the sun, they are litter bugs. We know them to be balls of ice and dust. And then when they get close to the sun, the ice melts or sublimates, and the material, that dirty, dusty material, is ejected off of the comet out into space. And as the comet moves around the sun, it leaves behind a trail of cosmic debris. And this debris remains confined to the plane of the comet's orbit, at least until in time the stream degrades and drifts apart. Gravitational perturbations by the planets are a major factor in shifting and breaking up a meteor stream. Tracking all of these influences is what meteor shower forecasting is all about. Now, when I mention to people that we might have a meteor shower, this probably is what people immediately think of as a meteor shower. You remember that show back in the 1960s, Lost in Space? This single-handedly set back astronomy and science by 100. Yeah, this, no, let me assure you, this is not a meteor shower. This is not, I mean, when we talk about meteor showers, we're talking about much, much smaller pieces. In the case of most of the annual meteor showers, the majority of visible meteors are caused by particles generally ranging in size from small pebbles to sand grains and weighing less than 1 or 2 grams. So, that's what we usually expect to see when we have meteor showers. The size of these particles are generally along those sizes and not those big boulders that you saw on that grade B science fiction TV show from the 1960s. Anyway, so will we see a meteor shower from Comet SW3 in the coming days ahead? Back in 2005, a technical paper was written by astronomers from the University of Western Ontario in London, Ontario, Canada. Paul Weigert here, Peter Brown, and Helen Shinge. But these three enlisted the aid of this guy, and he became a very important person for them. This guy was Jeremy Volbayon from France, who produced a sophisticated model for the formation and evolution of comet dust trails. So for Comet SW3, and he had a supercomputer to do this on, Volbayon created numerical simulations, and he used or had 2 million particle ejections simulated from 1801 until the year 2006. And Volbayon used in his calculations an ejection velocity. In other words, how quickly would a sand-sized particle be ejected off of the surface of Comet SW3? He calculated about 20 meters per second. His final analysis for the paper was that, looking at the future, no significant number of meteoroids released during the 1995 splitting is expected to encounter the Earth in 2022. In other words, according to Professor Volbayon, using his computer simulation, the comet SW3 would pass on by, but there would be no interaction with any of the material that came streaming out of the comet after it split in 1995, so no meteor shower. Oh, darn it. Well, still, out of curiosity, I tried to model the meteoroid stream associated with the 1995 breakup of Comet SW3 using some computer software. In fact, on the same computer that I'm talking to you right now, this software, an N-body integrator. So what I did was I took the orbital circumstances, the orbital elements of SW3, the comet when it broke apart in 1995, and then I created 20 comet samples. These samples were going to be part of the trail of meteoroids that the comet presumably released after it broke up in 1995. And I said, okay, I'm going to try and simulate the comet trail and the comet and its movement through the solar system and see how it interacted with our planet Earth. Did it interact, as Professor Volbayon said in his 2005 paper? Well, here is the animation. Now take a look. Here's Mercury. Here's the orbit of Venus. Here's our orbit, the orbit of the Earth. And this is the orbit of SW3. Remember, Remember, on the 31st of May, at this crossing point, that's where we interact with the orbit of the comet. So if the comet is here, or if any trail of meteoric debris is here, as the Earth is passing by this point in space, we will indeed see a meteor shower. If not, we don't. So let's start the animation. This is my animation now. Here comes the Earth. See it right here? The Earth is coming around in its orbit. Right over here, it reaches that point on May 31st, and there we go. There's the Earth at the crossing. But where's the comet? No comet. No trail of meteoroids. Bachagaloop! Professor Vabalyan was right. We're not going to interact. And soon you see, several months after the Earth was at that crossing point or passing nearby, here comes the comet, and here comes that trail of meteoric debris. So Vabalyan was right. No meteor shower in 2022. No big display in 2 weeks. And you're saying to yourself right now, well, if that be the case, then why the heck are we listening to you right now? We've been listening for 40 minutes, and you've been teasing us that there's going to be a meteor shower. Well, hold on for a moment. Hold on. In the physical, now this is what got me thinking after I did my own simulation. Initially I said, well, I guess he's right. We're not going to have a meteor shower. But then I got to thinking, and I said to myself, in the physical breakup of a comet nucleus, we just can't assume that its constituent particles are chiefly dust and sand grain sized. Indeed, they could be much larger. Large nugget-sized pebbles, even rocks the size of walnuts or ping pong balls. As you can see, before I showed you a person holding sand grains. Now we've got much bigger pieces to deal with. Now, how large particles are spatially distributed depends in part on the spin of the comet's nucleus. Yeah, just like the Earth and the other planets, a nucleus of a comet spins, turns on its axis. So depending upon the spin and also the location of its outgassing regions, as the nucleus is heated by sunlight, bits of dust and gas come loose and are spread outward. And the pressure, the push of sunlight, helps to force these particles back behind the comet. Now, the idea that light has push or pressure might sound a bit strange to you. If you hold your hand near an electric light or in the sunlight, you can't feel light pressing on it. But nevertheless, light does have pressure, and it's only noticeable when the light becomes extremely strong, as is near the sun, and only affects very small particles, like molecules of gas or dust or sand grains. This is called solar radiation pressure. Small particles are pushed away more rapidly by solar radiation pressure, regardless of the direction that they leave the comet's nucleus. And this pressure of sunlight helps to force just such dust particles to a position trailing behind the comet. But particles larger than grains of sand. Remember I showed you a few seconds ago, big, nugget-sized pieces of gravel. And as I said, they could be even as big as ping pong balls. Those large pieces are greatly unaffected by solar radiation pressure, like the big bad wolf. Solar radiation pressure can puff and blow on those big pieces, but they ain't going anywhere, folks. They're too heavy, and they pretty much stay in place. And here, then, is my argument. In a normal case, the smaller the particle, the more rapidly it can be ejected out into space from a comet, 20, 25, even 30 meters per second. If the particle is bigger, it's more massive, it's heavier, and then the ejection speed is slower, 10, maybe 15 meters per second. But this is not a normal case. This was the breakup of a comet nucleus, and when SW3 fragmented, particles of all sizes were probably ejected out at high speeds, even the big particles. And since solar radiation pressure has no effect on those big particles larger than sand grains, then they are likely large particles that are now sailing through space forward or out ahead of SW3. At least this is my contention. This is what I felt had happened. In other words, when we saw the other animation, all of the pieces of the comet and all of its pieces were trailing behind the comet. What I'm saying is that after the comet fractured, there were big pieces out in space that were in front of the comet. And if they were in front of the comet, they're moving in smaller orbits. And if they were moving in smaller orbits, they're closer to the sun. And if an object is closer to the sun and moving faster in its orbit, gravity insists upon that, then those particles will gradually spread out ahead of the comet in due time. So now we're going to rerun the animation. We're going to rerun everything, but this time the particles are assumed to be not behind the comet, but in front of the comet, okay? So here we go. And here comes the Earth, heading for the intersection point. But look at this. Look at this. Before the Earth has a chance to reach that area where the intersection point is, the Earth is now interacting between sample number 12 and sample number 13. Remember, I said I created a long trail of material, 20 different particles or comet proxies, if you will. And the Earth in this particular scenario ended up between comet number 12 and comet number 13. So what does that mean? And also look at the date, around the 28th of May. Well, okay, if it ended up between 12 and 13, you know what I did? I calculated the orbit of comet 12 and comet 13 and then put another 18 comets in between, because what I wanted to do was, what I wanted to get is an example of that particular section of the comet trail and how the Earth interacted with just that portion of the trail. Would it interact directly with other comet pieces? Well, here we go. Once again, here's the Earth, and here are those 20 comet samples representing, again, the trail of the meteoroids left behind by Comet SW3. And look at that. Look at that. We interacted with 5 of those 20 pieces, more or less indirectly. But that tells us that there would be an interaction, that we would actually see perhaps a display of meteoroids hitting the Earth's atmosphere on the night, 2 weeks from now, on the night of the 30th into the morning of the 31st of May. In fact, my calculation showed May 29.74 universal time. That's not important at the moment to you. But there's also, because this is not the most highly precise program that I was using, not to compare with some of the really supercomputers that the researchers use, there was a margin of error, I thought, of about a day and a half. So anytime between about the 28th to the 31st of May, I said, there could conceivably be a meteor shower caused by the breakup of Comet SW3. Well, after all of this, after doing this, I decided I'd write a paper. This happens, sometimes in your life, and we were in the midst of the pandemic, and I wasn't doing anything, and I no longer was doing television. So I said, okay, I'm going to write a technical paper, and I did, which was published in the Journal of the Royal Astronomical Society of Canada. Very, very prestigious publication. And the paper dealt with this question: will Comet 73P Schwassmann Wachmann 3 produce a meteor outburst in 2022? And the paper ran on for about 12 pages. And when you write a paper like this, and you have it distributed on a worldwide basis, other scientists, other people see it, read it, and they come up with their own concepts and ideas. And in this particular case, not one but 2 papers were written, one in Germany and one in Japan, investigating and looking into this and saying, hey, this guy Rao may have a point. He says that all of the material is forward of the comet, and maybe, just maybe, that just might provide us with a meteor shower. This German report was written by Hartwig Luthern, Rainier Alt, and Michael Jaeger. I have the highest regard for Luthern because he is a well-known calculator of comets and meteors. And here in Japan, another paper investigating the same thing. Meteor showers originated by 73P Schwassmann Wachmann, written by Sean Hori, Junichi Watanabe, and Mikao Sato. Well, I got to tell you something about Sato. Sato is right up there with probably the number one or most reputable of calculators for meteor showers. And here we have, Luthern and Sato working on the same problem, and both of them said, we were going to calculate when we think we may have a meteor shower. And do you want to know what? This is amazing. Two independent studies, and they came up with this. May 31.206, or 12:57 a.m. Eastern Daylight Time on May 31st. The two independent studies came within 4 minutes of each other. And I got to tell you, now, my calculation was off by about a day and a half from this. And I admit it. I mean, I am nothing compared. I'm not in the same league with these guys. I'm very happy that my suggestion in my paper was such that it led these guys to investigate on their own the possibility or prospects for a meteor shower. Very, very happy that they did this. But you want to know what made me even more happy? Here, my nemesis. This is Jeremy Vaubaillon. Now, you remember what Professor Vaubaillon wrote back in 2005. He said, we've looked at it with our fancy simulators. We looked at it from all different angles and directions and whatever. And to us, we are not going to see a meteor shower in 2022. Then my paper came out. And then others started to do calculations which showed that, hey, this is possible. Well, Professor Vaubaillon said, well, let's reconsider this. And he looked at the criteria, the parameters that I had mentioned in my research, my technical paper. And then he did a short study on his own. And in that study, he wrote this. In 2021, Joe Rao published a study showing that if the meteoroids are ejected at higher velocities, they will definitely cause a meteor outburst. Rao also explored the influence of the change of the comet's orbital elements. In this short study, we confirm Joe Rao's findings and go slightly further, exploring the conditions that make the shower possible as well as the observational optimization. Dr. Jeremy Vaubaillon. He wrote this. I read it, and I sent him an email immediately. And I said, Merci beaucoup, Professor Vaubaillon. Thank you. Thank you. Now he's seeing it from my vantage point and changed his the orbital parameters for his simulation. And now he's saying, yes, Rao may very well be right. That we may very well have a meteor shower. In fact, Vaubaillon wrote, just how many large particles can be expected to be ejected with velocities of 20 to 30 meters per second? Now, remember, I said a few moments ago, the large particles are more massive and heavy, so they don't go very fast usually when they're ejected from a comet, 10, maybe 15 meters per second. So how many large particles can be expected to be ejected with velocities higher than that? Typically, not many for most trails of meteoroids, but this 1995 meteor trail is unique. It was formed in the wake of a massive disruption of SW3. So, Vaubaillon said the required 25 to 30 meter per second velocity is a little on the high side, but not excessively so. And the ejection velocity range should just encompass the required value. In short, the more particles that were ejected at 25 to 30 meters per second, the greater an outburst of meteors will occur on May 31st. So now we know there probably will be a meteor shower. But now the next question, the $64,000 question, how many meteors are going to be visible? If you go outside that night at 12:57 a.m. Eastern Daylight Time on the morning of Tuesday, May 31st, and you go outside and you look up, how many shooting stars are you going to see that night? Is it going to be a lot? Is it going to be a little? How many? Well, here's the problem. We've never encountered this particular meteor trail before. If we've encountered it even just once, we could make at least a guesstimate as to what's going to happen again. We've never, ever hit this meteoroid trail before. So how could we possibly make a prediction? Well, maybe we can make a calibration with something similar. So now 5 years ago, in 2017, as the Earth was moving along in its orbit around the sun, we passed a trail of debris that Comet SW3 released in 1941. Now notice the main batch of material is within this cigar-shaped oval right here. And here's the trail of the Earth through space. In other words, we never came anywhere close to getting within that zone where most of the activity, most of the particles were. And again, this was ejected from the comet in 1941. We were, in fact, about 102,000 miles from the center of that trail of debris. And yet, even though we were that far away from the center of the trail, we still managed that night to see 5 meteors per hour. Those meteors were photographed, in fact, by the cameras for all sky meteor surveillance in California. Caught 5 of them in the span of 1 hour's time. Okay? So remember this now. This is 1941 material. Here's the Earth. We missed by 100,000 miles, but still managed to see 5 meteors per hour. Now, in 2 weeks from now, we're going to go through the trail of material that was put out into space after the comet shattered in 1995. Now, notice one interesting fact here is that in 2 weeks, we're going to go through the sweet spot. We're going to go through the zone where the most material happens to be. Now, in 2017, we interacted with material from 1941. That material from 1941 traveled 14 times around the sun. And those meteoroids had dispersed quite a bit from the time that they left the comet in 1941 until the time they were reached the Earth in 2017. This year, we're going to be encountering material shed in 1995. So that material, that stuff that came out pouring out of the comet in 1995 after it split up, has only traveled 5 times around the sun. So the debris is going to be much closer together as opposed to what we encountered in 1941. Now, in 2 weeks from now, we're going to come within 35,000 miles of the center of that 1995 material. 35,000 miles. That's about 3 times closer. So we saw 5 per hour in 2017, right? With the stuff from 1941. So if we're 3 times closer, or almost 3 times closer, we'll probably see 14 per hour. If we're going on a proportional basis from what we saw in 2017 to what we may see in 2022, 14 per hour. And is that really worth anything? 14? Are you going to stand outside that night, late at night, and watch for 14 shooting stars per hour? How many of that per hour? You'd have to be out there for a good, 14, 15, 16 minutes before you see even a single meteor. I mean, they're coming that spaced apart. That's no big deal, right? But here's the question. We're using 1941. We're using the material that was shed in 1941 as the proportional or scalability example here. But this is 1995. This zone coming after all of that dust, all of that, if you pardon the unprofessional word, schmutz, was pouring out into space after the comet split up. My question is, how much more concentrated is the material compared to 1941? And the fact is, as I said, we're going to go right through the zone, the main zone of material, in a couple of weeks. So what is the number? Is it 14 per hour? Or if it was 10 times more concentrated than in the 1941 ejection of material, that would mean, let's see, 10 times 14, the quick mathematics, that's 140 per hour. 140 shooting stars per hour. That's pretty darn good. That now places this potential outburst on the same level as the meteor showers we see in the summertime. The famous, I'm sure some of you have heard of the Perseid meteors. A lot of people discover them in August when they're out camping. That puts on a great display of shooting stars. And there's another display in December called the Geminids. If you care to stand outside on a cold winter's night in December and freeze, you would see that many meteors per hour. But you know, that would be one possibility. Now, you're probably looking at this right now and say to yourself, so where does he come into play here? This is, and I'm sure many of you know who this is. This is the happy little tree painter. This is Bob Ross. I'm sure many of you have seen him on PBS stations. He creates wonderful painting masterpieces in a matter of only a half an hour's time. He's great. I love him. You know why I love him? He has such a nice, soft voice. Now, if you ever listen to Bob Ross, this guy can put you to sleep in 15 minutes or less. But here's the thing. A lot of times when he's painting a picture, and he does it again in less than 30 minutes, halfway or three-quarters of the way through, he looks at you with that smile on his face, and he says, let's get crazy. Let's get crazy. And when he says that, all of a sudden, within a matter of the next few minutes, he covers the painting up with all kinds of trees or mountains or a big lake, or he'll scrape out a cabin in the woods somewhere. Let's get crazy. Well, now I'm using that motto, that credo, for this upcoming meteor shower. We said just now, what if the meteoroids were 10 times more concentrated in 1995 as compared to 1941? If that is the case, we'd see maybe 140 per hour. But let's get crazy. Let's assume instead of 10 times, let's assume it's 100 times greater than 1941. So to do a calculation, 14 times 100, that would give us 1,400 shooting stars per hour. The official designation of a meteor storm is 1,000 per hour. This would turn into a true meteor storm. Is it possible? I don't know. We will not know until the night when we actually come right straight on through that trail of debris, and just how many meteoroids are out there will determine how many shooting stars we will see that particular night. Now, this is an important diagram to study. This diagram shows the Earth moving through space from left to right. Now, notice on the upper right, we have the paths of the Leonid meteor shower. That's a shower that occurs every year in November. And when these meteors interact with the Earth, they hit the Earth almost head on and move at an ultra fast speed through our atmosphere of 72 kilometers a second. That's 45 miles per second. That is fast. And atmospheric friction releases the kinetic energy of the object in a short-lived flash of light. By the way, the energy released per gram of the weight of a meteoroid far exceeds the energy efficiency of the most powerful man-made explosives. So, if you have a Leonid meteoroid striking the Earth's atmosphere at 72 kilometers per second, even one the size of a pea can create a bright, beautiful, incandescent trail in the sky. And that's why when you go out to look for Leonid meteors in November, even if there's only a few, or sometimes there's a whole heck of a lot, you can base your money, you can put your money down that every one of those meteors is going to be a bright and very visible streak in the sky. But now, the SW3 meteors, the meteors that we're expecting in 2 weeks, look at their movement. The meteors that were loosed from SW3, they're moving in the same direction as the Earth. Only those particles that can catch up to the Earth will have a chance to create a visible streak, but at 16 kilometers per second, only 10 miles per hour. They're moving less than a quarter as fast. So a proportion of the meteors that we are looking for may be very faint or not visible at all. In other words, if you're trying to see this meteor shower 2 weeks from tonight, and you're on a street corner with street lights around or in a brightly lit city, you may not see very many, if any at all, because the street lights may just overwhelm the majority of those meteors. Even the meteor shower that we saw, the storm of meteors that we saw with Comet Biela in 1872, they were described as slow, faint, and evanescent. Have you ever heard that word before, evanescent? That's a 19th century word if I ever heard one. I looked it up in the dictionary, and found that evanescent means transitory, fleeting, vanishing. So maybe, just maybe, this may be a disappointment. If a lot of these meteors are faint, there isn't going to be much of a show, even if we do have 1,000 of them per hour. But some of these meteors in 1872 were said to exceed first magnitude. First magnitude is the brightest stars in the sky, often appearing red with trains of orange sparks. So yeah, maybe a good number of these will be quite interesting, quite bright, quite spectacular to see. Even though the majority may be faint, some of them may be very spectacular on their own. And in fact, about 10 years ago, a gentleman by the name of Pierre Martin, who lives in Bootland Farm, Ontario, was watching for the SW3 meteors one of the years when they were supposed to be around in 2011, and he said he saw a single gorgeous meteor. It was magnitude -1, which is brighter than, well, as bright as the brightest star in the sky, Sirius, the dog star, golden yellow, and it left behind a thick wake. In other words, it left behind a trail or a visible train in the sky that remained for several seconds at least after the meteor itself had flashed on by. That would be nice to see, wouldn't it? We saw a bunch of those. That certainly would make the night well worthwhile. Where would the meteors be? Well, if you're out that night looking, they would have. They originally, when that guy who claimed he saw the meteor shower in 1930, the guy with the sensitive eyes, he he said that they came from the constellation of Hercules near the star Tau, Tau. So they were known as the Tau Herculids. But we know now that this meteor shower, if it does show up in a couple of weeks, is more than likely to appear in the sky within the boundaries of this sky, Boötes, the herdsman. More on him in a moment. This is a map showing the region of the world that will be looking skyward, will be favorably placed to see the upcoming meteor shower in 2 weeks. These are altitude markers. If you are in Baja California, in Mexico, the point where the meteors would seem to streak from, the radiation point, if you will be directly overhead. Right overhead! And supposedly the meteors would be firing out in all directions from that particular spot in the sky. But then if you get away from Baja, the shower radiant gets lower in the sky. So this is the 80-degree marker. Here's 70, 60. Now we here in New York or on Long Island will be between the 50-degree marker and the 60-degree marker. So the meteor radiant, the point in the sky where they're going to come streaking out from, will be 55 degrees up above the horizon. And you're saying to yourself, well, how high is that? I don't know how to measure. Well, of course you can measure 55 degrees. You have the measuring device with you. It's your fist. Make a fist. Hold it out at arm's length. Now put the bottom of that fist on the horizon. The top part of your fist measures 10 degrees. So that's how high up 10 degrees is. One fist. So for 55 degrees, you'd go one fist, two fists, three fists, four fists like this girl, or maybe as this young man is doing, five, and add another half, 5.5 fists above the horizon. Measure it out for yourself. See how high up 5.5 fists is. That's pretty darn high up in the sky. But to help you out also, make sure you're looking in the direction of Arcturus, and I'll show you a star map. Oh, Joe! Oh, please! A lot of people don't really know how to read a star map. People who are into astrology, my goodness, the signs of the zodiac. If I gave them $10 and said, here, I'm going to give you this $10 bill. I'm going to take you outside right now. Find me Sagittarius, or find me Capricornus, the sea goat. Find me and Libra, the scales, or Virgo. They wouldn't know where to look. People are baffled by the constellations. Well, here's how you find Arcturus, okay? Go out and look for the Big Dipper. You've seen the Big Dipper. Just look toward the northern part of the sky. At this time of the year, the Dipper is high, almost overhead at sunset. But at 1 o'clock in the morning, on May 31st, 2 weeks from tonight, the Dipper will be in the western part of the sky. There it is. And you've seen it, I'm sure, many times in your life. 4 stars make up the bowl, and 3 stars make up the handle. All right? Now, take the handle of the Big Dipper and stretch a line out through the handle. Follow the arc to Arcturus. Arcturus will be about halfway up in the western sky. Arcturus is one of the brightest and most colorful stars in the sky. So at 1 o'clock in the morning on May 31st, if you look halfway up in the western part of the sky, you will most definitely see Arcturus. There's nothing like it anywhere else in the general vicinity. Shining again with a yellowish orange glow, shining brighter than just about any other star up in the sky at that hour. And once you found Arcturus, you're home free, because not too far away is the apparent source of the shooting stars, of the meteors that will be visible that night. Will there be a lot? Will there be a little? We don't know. We can't say. But do you want to be in bed at 1 a.m. on May 31st and actually end up missing a potential storm of shooting stars, perhaps seeing more shooting stars than you've seen in your entire life? Now, if you're going to go out and look, make a special case to get as far away from the bright lights as you possibly can. Maybe, since it is the tail end of the Memorial Day weekend, make a note. Maybe you say to yourself, well, this Memorial Day, I'm going to go up into the Catskills, or maybe the Berkshires, or the Poconos, or even as far north as the Adirondacks, where the skies are much darker. There are no big cities, and where you can see a lot of stars in the sky. And the best news of all, we had a full moon last night. I don't know how many of you saw the total eclipse that occurred, but you can only have a total eclipse of the moon at full moon. That's important to note, because this meteor shower now is 2 weeks away. And in 2 weeks, the moon isn't going to be full. It's going to be the opposite phase. It will be a new moon. It will be dark. In fact, when the meteor shower is occurring, it will be below our horizon. It'll just be a skinny little sliver. You will not have to worry about the moon's light interfering with your observation of the meteor shower. So go out and take a look. Now, I'm going to close this talk by saying that I'm excited. I'm excited to see what's going to happen, though I have to admit that I won't be holding my breath. You see, meteor showers are notoriously fickle, and it's possible that nothing at all will occur at the appointed time, which isn't bad. If you take my advice and you decide, I'm going to listen to Joe and I'm going to go someplace where it's nice and dark and where I can see a lot of stars, well, when was the last time you did that? Did you ever do it at all? So even if you don't see a single meteor, if you're in a place where you can look up at the sky and see a sky full of stars, that in itself is a fitting consolation prize. It's a beautiful thing, especially so if you're away from the bright lights of the city and can see, for example, the Milky Way in the sky. So maybe, just maybe, we'll all go out and not see any meteor shower at all. But I make the case for this. If historical patterns are any guide, we are long overdue for an event such as this, because over the last couple of centuries, it seems that a new, strong shower of meteors emerges seemingly from nowhere with some frequency. Particularly noteworthy are the Lyrid meteors that appeared in 1803. Normally, this shower comes every year in April, isn't anything to write home about. But for whatever reason, in 1803, we must have hit a clump of thicker and heavier than normal dust and debris, which produced a storm of shooting stars. The church bell in Richmond, Virginia was rung to awaken everybody. Get out of your beds, come outside, take a look. It's the end of the world. That's how many meteors were seen in 1803 on that amazing night. Or the Andromedids in 1872. This is the meteor shower that came from the splitting of that comet Biela, and no one knew it was that. Nobody knew. It was a surprise. People looking outside on that night, November 27th, 1872, and they seeing meteors falling every which way. One of the greatest astronomers of all time in the late 19th century in France, Camille Flammarion, the Carl Sagan of France, and he had traveled from France to Italy because he had been invited to have an audience with the Pope, Pope Pius IX. And when he made that long, arduous trip from Paris to Venice, What did Flammarion do? He said, well, I'm going to have a busy day tomorrow. I'm just going to stand outside, look at the beautiful sunset, and then I'm going to go to sleep. He was in bed. He was in sleep when this magnificent display of shooting stars took place. Oh, what an embarrassment. The next day, when he went to the Vatican Observatory, the head of the observatory, Father Angelo Secchi, told Flammarion, oh, what you missed last night. And Flammarion said, how did you find out? And the director of the observatory, Father Secchi, he said, well, I was having my evening meal, and I heard a knock at the door. I opened it up. I saw this gentleman I never saw before in my life. I said, yes, can I help you? And the gentleman said, Monsignor, can you answer me a question? He said, yes, what is it? He said, why are the stars falling from the sky? And the father looked up, and he saw this magnificent display. Surprise! And even worse for Flammarion, when he met with the Pope, the first words out of the Pope's mouth was, did you see the shower of Diana last night? Diana was the goddess of the sky. So Flammarion missed it. He missed it. He was in bed. Oh, how terrible. Or the Jacobinid shower, another surprise in 1933 when we crossed the path of, or crossed through the trail of Comet Jacobini-Zinner. And it was written that people in Portugal, in Spain, in Ireland, all on their knees looking up because the meteors were so spectacular. Meteors were so incredible that they thought, just like all the other occasions, the world was coming to an end. So, I maintain this, folks. We have not had a surprise meteor shower pop up in quite a while. Maybe this is the shot. 2 weeks from now, I'm going to be outside watching, waiting, looking. My question is, will you? Well, we'll see. We'll see what happens. That's what makes watching shooting stars and meteor showers fun. Sometimes you don't know exactly what's going to happen. And so we'll all look and we'll all see whether or not there'll be a meteor display coming up in 2 weeks with this spectacular thing. Again, remember the date will be actually late Monday night, early Tuesday morning, May 31st, just before 1 a.m., 12:57 a.m. That's when we should be hitting the peak of the shower. And if there's anything to the possibility of seeing a spectacular display, that would be the time to be out and the time to look and the time to watch. And let's hope that the weather will be on our side that night and we'll all see a nice pyrotechnics display courtesy of Mother Nature. I thank all of you for coming tonight from all the libraries that have participated in tonight's session. And all I can tell you is just go out and keep looking up and enjoy the sky while we still have it.